The cliffhanger. From where he stands, one step toward the cliff would send the drunken man over the edge. He takes random steps, either toward or away from the cliff. At any step, his probability of taking a step away is 2/3, of a step toward the cliff 1/3. What is his chance of escaping the cliff? So let's start by drawing the x-axis where this random walk occurs. Here, x is equal to 0 is going to represent the cliff. We call it an absorbing state since it terminates the random walk. The drunken man starts at x is equal to 1. Let's indicate that with this blue dot. And we have other states, x is equal to 2, 3, etc., up to infinity. Now, at every possible state, the random walker can either take a step to the right with a probability of p is equal to 2/3, or he can take a step to the left with a probability of q equal to 1 minus p equal to 1/3. Okay, so in this problem, it's actually easier to find the probability of falling over the edge first, and then subtract that out of 1 to get the escape probability. Let's establish some notation. Consider an arbitrary position x is equal to I, then let's denote the probability of falling from that state to be pi. So for example, p1 would indicate the probability of falling if starting from x is equal to 1. In that case, what can happen in the next step? He either takes a step to the right with a probability of p and finds himself with a chance p2 of falling over the edge, or he takes a step to the left with a probability of q and finds himself with a chance p0 of falling. Again, x is equal to 0 is a boundary condition, and we know that p0 must be 1 because if he finds himself at x is equal to 0, he has already fallen over the edge. Okay, but how can we find p2? And this is the key part in this problem. We need to try to express it in terms of p1. We've already established that if the drunken man finds himself at x is equal to 1, then his chance of failure is p1. But what is the chance he goes from x is equal to 2 to x is equal to 1? Actually, it's again p1, because if we just shift our x-axis, then it is equivalent to going from 1 to 0. Just changing the indices of where he stands should not change the probabilities, so we say that going from 2 to 1 should be p1 as well. Now we claim that the events of going from 2 to 1 versus going from 1 to 0 are independent. Also, both of those events have to happen for the walker to go from 2 to 0. Therefore, we can write p2 is equal to p1 squared. Next, let's cast this tree into an equation. p1 is equal to q times p0 plus p times p2. Here we use the law of total expectation, or you can think of this as the expected value of p1. Substituting q, p0, and p2 gives p1 equal to 1 minus p plus p times p1 squared. Now let's rearrange the above formula. This is just a quadratic equation where the only unknown is p1. Let's solve for the two possible roots. Okay, we got our two solutions. One solution gives just 1, the other one gives q over p. Both of these solutions are correct depending on what value of p we're dealing with. To explain that, let's draw a plot of p1 versus small p. If p is equal to 1/2, then both solutions agree and they give p1 equal to 1. If p is smaller than 1/2, then this solution gives a probability larger than 1, which is impossible, So we take the other solution for this range, which is 1. The remaining range for the other solution is p larger than 1 over 2, which decreases from 1 to 0. So in our problem, p is equal to 2 over 3, then we use this solution. The probability of escaping is 1 minus p1 equal to 1 minus q over p, which is equal to 1 over 2. And this is the answer to the problem. Interestingly, even though the walker has a bias or a drift to walk away from the cliff, the probability of escape is only 1 over 2. Now, I want to mention two other related questions to this problem that we can answer easily given our solution. First, what would be the failure of the walker if it started at arbitrary x is equal to I instead of x is equal to 1? Well, we can use the same logic here that we used to find the p2. We know that the walker needs to somehow reach the previous state, which has a probability of q over p. This has to happen I times, which are all independent from each other. Therefore, we can again just multiply them, giving pi equal to q over p to the power of I. Another related question is the following. This time, imagine a fair random walker with p equal to 1 over 2 starting at x is equal to 0. So steps to the right and left are equally probable. The question is, what is the probability it comes back to x is equal to 0? Well, we know that it definitely comes back to x is equal to 0 if it were to start from x is equal to 1, as we saw in the original problem. We can say the same thing for x is equal to minus 1, as it is the mirror image of the x is equal to 1 case. Therefore, p0 is equal to p times p1 plus p times p minus 1, which is equal to 1. So the walker definitely comes back to its origin if it is unbiased. I find these problems to be quite important as these results can be helpful in other problems.